Okay, I've got the nod to start. Oh, I'm so loud. So we're going to start with a warm-up so that you can remember everything that we did. So we can warm up. First, did you do your homework and did it all go okay? Yeah, so you can tell me the meaning of, let's do the hardest one, d by dx, f squared of x evaluated at 1. Okay, brave souls, what does this mean? Flipping back. Yeah, excellent, excellent. So we start with 2 individuals. They each are having offspring described by Pgfs, and then we're going to add up the total number of offspring and the expected value of the total is given by this, right? Okay, super. If you can do that one, you can do all the rest of them, I'm sure. Another warm-up question. We did this one in class. Pgf, this will illustrate something I want to show you. For a process where you always have exactly 1 offspring, I think Lucy brought this one up in class, right? Yesterday? Was it just yesterday? It feels like several days ago, but it was yesterday. Several lifetimes of learning ago. So what's the Pgf if we always have exactly 1 offspring? I think I heard an X over there. Yeah, good, excellent. X. Okay, what if we have exactly, actually I'm going to call this A, B, exactly N offspring. Excellent, X to the N. I don't know, let's call it G. Okay, here's what I wanted to point out. Suppose I have N identical copies of process A. What's the Pgf for that case? We want the sum of all of the, and we want all the offspring. Yeah. It's also X to the N, right? Yeah, because it would be N copies of that. So these are the same. And that's kind of right. Like if we have exactly N copies, the picture is like this. How many offspring? And if we have N identical copies of this thing, the picture is like this. But the outcome of how many offspring we have is exactly the same. Okay, great. We're going to use those tricks in a moment. Last bit of review though. Part 3. I've got a random variable x with the following probability mass function. 0 offspring with probability 1/8. 1 with probability 1/2. 2 with probability 3/8. What's the probability that a branching process in which every individual follows this goes extinct? This is when you're going to need to actually do a little pen and paper work. If you can factor, you can do this one. It's the extinction probability. Of a branching process starting with 1 individual where everyone has offspring according to this probability distribution. So do you remember the formula for this one? Yeah. So you need to write F. That's good. I see lots of pencils moving. I did not get 4, 9, but I could have factored wrong. We can both do. I skipped some steps here. Like I did stuff in my head, which, you know, I should never do. Yeah, I think you might be right, actually. Yeah, mine is wrong. I think, is anyone else getting 4 9s? No, is it not working nicely? Shoot, sorry. I got 1/3, but I thought I just found my mistake, but maybe not. Okay, so we can do it like Chris, we can have some votes here. Anyone else for 1/3? You got 1/3 too? 1/3? Okay, sorry. Yeah, so we should get, you know, x equals 1/8 plus 1/2 x plus 3/8 x squared, and then you can multiply everything by 8 and then make it quadratic and factor it, and you should end up with x equals 1, which you always get, and x equals 1/3. And then you take the smaller value, that's your extinction probability. Here we're going to get 3x minus 1, right? Okay, good. Everyone okay with that? Ish? Those of us that could remember how to factor, not happy? You're frowning, Chris? No, you're... Yeah, that's right. Yeah. Yeah, exactly. For any set of values that are a probability that sum to 1. Yes, yeah. Okay. So let's do a few more really common Pgfs, which will lead us to an awesome result. So one is flip a coin. That's a Bernoulli variable. But our coin isn't fair. So our random variable x will say 0 and 1, where this is a head and this is a tail. 1 with probability p, and 0 with probability 1 minus p. So what's f of x? Kind of too easy at this point, right? We're just going to write down 1 minus p dx. Excellent. Okay. Your pros now. So if you can do 1 coin, let's do n coins. So flip n coins and count how many heads. This is 2. That is a binomial variable. I guess I should say here, count heads. Or tails, really, it doesn't matter. Total number of heads. So does anyone remember the formula for the probability that I get k heads if I flipped n coins? Yeah, excellent. N choose k. Beautiful. Okay, so if that's pk, write out like the first 3 terms of the probability generating function. I mean, I've given you this huge notational clue by calling it little p sub k, right? That's the probability of 0. So you just basically plug this in. Yeah, exactly. So, and then, you know, maybe I won't even write that all out because it's a kind of a mess. But after one little tiny manipulation, we'll get 1 minus p to the n. I'm going to write it as 1 minus p to the n minus 1 n px. No, I want the n at front. For my own nefarious reasons, I'm moving things around here. 1 minus p to the n minus 2, p squared x squared. This is probably not exactly what you wrote down, but it's the same. I just wiggled things around. But I wrote it down this way so that you could see my coefficients are 1, n choose 2. And then I've got something to the n, something to the n minus 1, something to the n minus 2. And then I've got the px, p squared, x squared, etc. So for instance, if there were only 3 terms, it would be 1, 2, 1. The coefficients are going to go back down, or 1, 4, 6, 4, 1. So can you write this for me in a simpler form? I'm not sure if you just said it. Lovely. Quantity to the n. Yeah, so if you expanded this out, you get that 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, and then all the various powers. Yeah? Okay. Tell me why you could have written this down without doing all of this work. It's like beauty of mathematics, how you can get to the same answer so many different ways. Exactly. This is flip 1 coin. This is flip n coins. And identical copies of the same process. Isn't that nice? So beautiful. Okay, so now we've done binomial Bernoulli, and then the one that we're actually going to use for PopGen is the Poisson distribution, of course. So we'll do the Poisson distribution with mean lambda. Okay. Probability experts, P sub k for Poisson distribution, probability of k. It's e to the negative lambda, lambda to the k, k factorial, right? Okay, sub that in and write out your probability generating function. Do a few terms in your notes. And once you've done a few terms, write it this way for me. You don't really have to do a few terms, but sometimes I feel like it just helps you get a feel for what the sum is, the sequence is going to look like. Yeah, that's right. So let's go e to the minus lambda. We have a lambda. Well, for the first time that we see it, let's do lambda to the k, k factorial, and it's all times x to the k, right? And then we notice, well, actually, I'll do another line. Let's do another line. I'm going to bring the negative lambda out. Lambda x to the k over k factorial. You're starting to get excited because this is so pretty. Because what's that? Biologists maybe don't know. Yeah, this is an exponential. This is, in fact, I think the most sensible way to define the exponential function. But that's like another lecture. So this is e to the lambda k, or lambda x, by definition, right? And so we get e to the negative lambda, 1 minus x is how I usually write it. I'm going to give you a box. Okay. So what's neat about these things is that we take these infinite series and then they collapse down to these really compact, lovely expressions for some of the basic probability generating functions that we use all the time. And we're going to use this one right now, the way that Haldane did. Okay? So I'll take the simplest possible model again to look at extinction. Maybe not the simplest possible, but the simplest realistic model. So haploid, asexuals, but because it's mathematically simple, not because it's biologically reasonable, we will use Poisson distributed offspring. And the mean number of offspring, 1 plus s. So your canonical beneficial mutation. All right, can you write the Pgf describing this branching process? I mean, it's basically this, right? We're going to put in the new lambda. So e to the negative 1 plus s. Okay, and then Haldane wanted to find the extinction probability. E to the negative 1 plus s, 1 minus x. And although Haldane's result is super famous, it's actually like there's so many different ways that you could Taylor series this guy or try to figure out the result from here that it's not obvious when you try it the first time. So the first thing to do now is probably to write it in terms of the fixation probability instead of extinction. Later, we're going to make the assumption that, sorry, we're not really going to assume that S is small. We're actually going to assume that fixation is unlikely, because it usually is with small mutations, small magnitude mutations. But for now, let's just do this. One plus S pi. And then the next thing you want to do is take the log of both sides, natural logarithm. 1 minus, thank you. Okay, and then at this is the point at which Haldane reasons that pi is probably small. So for small numbers, we can use Taylor series ln 1 minus x, which I don't expect you guys all know, but you could do it. And it is negative x minus x squared over 2 minus higher order terms, in fact. So where we make the approximation here is we say ln of 1 minus pi is approximately negative pi minus pi squared over 2. So what we actually assume is that pi cubed is negligible. That says negligible. Negligible. Yep. So putting that in, I'll go back. In fact, you guys can do it now. Do the rest. Tell me what pi is. Yeah, excellent. And you got another root as well, right? 0, yeah. So you do a tiny little bit of algebra and you get pi equals 0 or pi equals 2s. And the pi equals 0, that's just like x equals 1, right? So that's our trivial solution. We can ignore it. And this is our extinction probability. Or I should say our fixation probability. And you've all seen, right, the Haldane's 2s approximation? Yeah, no, in your intro course. So for small s, it's usually taught when s is small, we can assume that the fixation probability of a beneficial mutation is 2s. But now you can see, we actually don't assume that s is small. What we fundamentally assume is that the fixation probability cubed is negligible, small enough that we can ignore it, right? Which means that s is small. Okay, so now we are up to speed with Haldane. Do you know who developed branching processes and this first extinction work? Galton and Watson. Galton was a cousin of Darwin, a Victorian polymath, where a polymath is someone who does everything like those Victorian gentlemen did because they didn't have anything else to do. They could be good at math and write books and explore the world and whatever. And so Galton was a polymath, and he was interested in the extinction of surnames. The upper class surnames appeared to Galton to be going extinct seriously faster than the lower class surnames. And he wanted to know how we could predict the extinction of surnames. And he posted a kind of cry for help in the scholarly journal of the day. And then Watson was a very smart priest or pastor or Anglican priest or something, vicar, who in his spare time did math. And then they got together and answered this pressing question, and they developed branching processes on the way there. So there you go, Galton, Watson. So this Poisson distributed offspring branching process is called the Galton-Watson process. Yeah. Yeah, I guess it must be from whatever math means in Greek, which I don't know. Or it could just because it's because math is the best. It could be that. Okay, Haldane, we did that. So, multi-type branching processes. New topic. So we're going to extend branching processes because you're so comfortable with them. We're ready to move on to like grad work now. So multi-type branching processes. Or multi-type probability generating functions. To learn. Yeah. So polymath, you learn everything. Yeah. Okay. So sometimes we need to care about different types of offspring. Very often, in fact. And you can do branching processes and write a generating function with different types. It extends really naturally. So I'm going to just teach you by example. We need a new dummy variable for every different type. So in my example, I'm going to have a mutant, dummy variable m, and a wild type. And I have to tell you what the offspring distributions are like, just like I would in a single type. But of course, generically, the different types can give birth to their own type or a different type. So in my example, each W they can produce a lot of different things. Let's say 0 offspring with probability 1 minus P. So P is like the probability that you mature and have offspring. Or they maybe produce 2 wild type because they're a bacterium with probability P 1 minus mu squared. Neither of them mutate. Or maybe they produce 1 wild type and 1 mutant. 2P 1 minus mu mu. Or maybe they produce 2 mutants. That should add up. And then each mutant, we're going to make this a little easier. In my toy model, the mutants don't mutate anymore. So the mutant can either die or produce 2 mutants. So the way that we set up a multi-type probability generating function, it seems a little head scratchy at first, but then once you see it, it makes sense. So we write, I guess I should start here. We have to write a probability generating function for each type. So we do f of the wild type, and it will be a function of 2 variables, so 2 dummy variables, right? And it's going to be the sum of PAB m to the A, W to the B. And this PAB, you can kind of figure out what it's going to have to be, right? It's sort of, yeah, the probability that you have A mutants and B wild type. Just exactly analogously to what we did when there was only one type. So probability A mutant and B wild type offspring. So you should be able to write FW it's going to have 1, 2, 3, 4 terms. So go for it. Yeah, 1 minus P, coefficient of m to the 0, W to the 0. Yeah, exactly. And then we'll have the P1 minus mu squared coefficient of, yeah, beautiful, etc. I guess we'll put them all up here. 2p 1 minus mu mu Wm and p mu squared. Yep, and then the other one is pretty easy. You can likewise write a probability generating function for the mutant. And this guy is really easy, 1 minus p plus pm squared. Yeah? Yeah? No, in my model, the mutant, yeah. Yeah. From here, yeah, the mutant just either dies or produces 2D mutants. So it's just a toy model. Okay, no, so I haven't told you yet how we get the extinction probability, because now we have these two generating functions, and you have to solve them simultaneously, 2 equations, 2 unknowns. So we need to find a fixed point in the same way. Because there's not time, I'm not going to give you the proof that this is what works, but you could find it in any set of lecture notes, probably about multi-type generating functions. So to get the extinction probability, we solve the system. That 1 second. Excellent segue. That's exactly the natural question. Yeah, so we're going to have Fm of x, y, say, equals, and F wild type, let's do wild type first, that's what I've been doing, of x, y. So the first question is, what goes here? And it turns out the thing that works is to set this one equal to x and this one equal to y. So it's a fixed point of the whole system in that way. You find 2 points, x and y, 2 numbers, that when you sub them both into the left side of the equation, this equation will give you x and this equation will give you y. And then the next natural question is, why do we have 2 extinction probabilities? Neither of them is trivial. So this is some branching process. What's the initial condition for this branching process? I haven't told you, right? You got to start with one person, one individual. You'd think it might be the wild type, but it could be the mutant. Wouldn't be that interesting to study. Does that give you a clue to what these might mean? Yeah. So this is the extinction probability if we start with a single mutant. And this is the extinction probability if we start with a single wild type. Sorry, don't write that down. Wild type mutant. Yeah, but you can't just, you have to solve them simultaneously and find them both. But then you usually only care about one, or often. So this is, let me actually write a whole new line. X, extinction if the lineage starts with one wild type, and Y, extinction if the lineage starts with one mutant individual. So you get 2 extinction probabilities. They're often very different. This equation, in this case, you don't actually need to solve them simultaneously because physicists, they decouple, so we can actually just solve this one first and then sub that in. But generically, you do need to. Okay. Questions? Excellent questions as we go, so thank you for those. I've done this a lot, so applications for this. Can you think of applications for multi-type branching process? So you want something where a couple different steps might be required. So offspring of different types. So a canonical example is development of antibiotic resistance, for example. So the wild type is going along, having its offspring, and if it mutates, then there's resistance, then the offspring distribution changes for the resistant type. And you could have multiple steps. So you could require 3 mutations and have 3 or 4 dummy variables. And the mutational trajectory has to go through all those steps to get to the final guy who is fully resistant to the antibiotic or who is a novel coronavirus that can jump into humans. You may need 3 or 4 mutations to do that. Those kinds of questions we can address with this. Chris? Because here's the branching process starting with a single wild type that we care about, but somewhere along here a mutation happens. And if all of these, this is a really good question actually, I'm glad you asked it and I should have included it. If all of these go extinct, but this continues, the lineage is not extinct. So for the lineage, yeah, I should have said this. In these multi-type branching processes, extinction means the whole process goes to 0, right? Yep. Yeah, thank you. So let me just, even though I'm probably beyond the invisible border here, I will add extinction. Both of them are extinction of the entire lineage, both types. But also I think you have the right intuition that we don't need X to know the extinction of Y. Here we don't need to care about this process of the wild type to figure out the extinction probability if we start with a mutant, because the mutants never go back. And that comes out in the math, that we don't actually need.
Wait, you say you don't need to know whether
You don't need
W's go extinct, they can never make a man.
If,
it seems like you would need
but
to
why, yeah, why is the extinction if the lineage starts with 1 mutant? To get that, you don't need to know anything about the wild type in this case, yeah. Okay, so more questions? Good, okay. So now we will do another extension. Now that you're multi-type experts, we go on to like week 4 of this grad course. You should be feeling very proud of yourselves, which is continuous time branching processes. And this came up in the questions. I think it might have been Chris. What if we care when things happen, not just if they happen? And this is the first step towards that. We won't really answer that question, but I'll at least show you how we do it, how we approach it. Pgfs in continuous time. Maybe it should be capital. It's a heading. So what if we care about timing? Or also, what if our organism doesn't have discrete generations, isn't modeled well by discrete generations? We want continuous time. So then it's pretty simple. Again, once you've seen it, you're like, oh, that makes sense. Instead of pk, probability that you have k offspring, we look at the whole lineage and define p sub k of t, probability that there are k individuals in the entire lineage at time t. I will put entire lineage, just because that's the one thing that's a little bit weird about this. And then we write the usual probability generating function. But f of x depends on t now. Probability that we have 0 individuals in the lineage right now. Probability we have 1 individual in the lineage right now. And I'm going to use that as the coefficient of x, etc. Yeah, okay, so we're going to derive one. This is actually like really kind of cool math. So I hope you will like it too. I'll do maybe the simplest case we can do here, which would be a pure birth process. So no one ever dies. Every individual just goes along in time, and with probability, or at rate b, they give birth to one offspring, and there's 2 of them. So and on it goes. Obviously, this doesn't go extinct, so it's not really interesting from the extinction probability point of view, but it's a really nice example we can use to learn about how to write down a continuous time branching process, okay? Each individual gives birth at rate b per unit time. Okay, so what's the probability a new individual is produced in time step delta t? Let's say if we have 1 individual in the lineage. So that's pretty easy. We're just converting a rate to a probability, right? So b delta t. And if we have n individuals in the lineage, they could all give birth, so nb delta t. Okay. So the trick to deriving these things is to just have your probability generating function at time t, which looks exactly like this. And then we're just going to step forward delta t and make changes, whatever we need to change between t and delta t. So if the probability generating function at t looks like p0 plus p1 x plus, I guess, of t, x plus p2 of tx squared. The question is, what is f of x t plus delta t? Okay, so it's going to be exactly the same as it was, except for the things that change. So exactly the thing that it was. And what can change? A birth is the only thing that can change. But to figure out the probability that a birth happens, it's different for each of these, right? So we have a whole bunch of different cases that can happen. So we can condition, for those of you that have done a probability course, right? If there's 1 individual, the rate is this. If there's 2 individuals, the rate is this, etc. Okay, so let's do that. plus changes. Probability, there's one individual. And there's a birth. These long blackboards are wonderful. Okay, probably there's one individual and there's a birth. If this happens, which of these coefficients would change? P1 would change, going up or going down? Going down. And who else is changing? P2, exactly. There's one individual and there's a birth, then there's a little bit less probability here and a little bit more probability here. Yeah? So we have to take this. This is like bad math notation. We want to subtract that little piece of probability from the coefficient of x and add it to the coefficient of x squared. Yeah? Yep. Yep, very good question. So the question was, we're assuming that only one birth can happen at a time. I'm going to make that assumption, and it's going to be valid because you can probably see this coming already, right? I'm going to take the limit as delta t goes to 0, and then that probability that they happen simultaneously will vanish. Yep, good question. Okay, so this is what we do if there's one individual now, and then we have to do the same kind of thing if there's two individuals now and three and so on. And if there's two individuals now, I'm going to take some probability from here and put it there, right, all the way along. So probability, there's one individual now and there's a birth. That's the probability of the birth, so it would be P1 times this. Yeah? So again, this is really bad notation. Okay, so putting all that together, I'll move back over. I actually find this, this part of my work so satisfying because I start with this like physical model like this of what's happening, and then just do all these little steps where I'm moving pieces of probability. I'm thinking like it's just, I'm not just following some rules on the page for how to solve these things. I'm developing the new mathematics, right? So from first principles, we keep going. So we have f of x t plus delta t, f of x t, and then I have take b, take p1. I'm just going to drop, well, I won't. b delta t, subtract it from the coefficient of x, add it to the coefficient of x squared, and then take P2, then our birth rate is 2b delta t. Subtract it from the coefficient. We had 2 guys, but now we're going to have 3. Yeah? Okay, and then I'm just going to collapse those in summation notation. And while we're at it, because you can all see this coming, right? This is coming over. I've got delta t everywhere, factoring it out, bringing it over. So we get, unsurprisingly, x t plus delta t minus f of x t all over delta t. And I will write those sums for us. Sum on I p sub I of t. Let's drop the t's because we're just gonna have to keep writing them out over and over again. X to the I plus 1, sum on I p sub I, x to the I. So I've just put the positive terms before the negative terms. In case you're confused, this guy went over here and these guys came here. I'm being a little bit hand wavy with my eyes. These actually go from 0 to infinity because the zeroth terms we can put them in because the i's are there. It all works out. Okay. The left side, looking pretty lovely. We're all good with that. Yes, we're smiling. The right side also really lovely. Let me show you why. Oh, I could just lose that actually. Start fresh. Generically, f of x, we'll take out the t for in the moment, p0 plus p1x plus p2x squared plus, write for me di-f di-x. In summation notation. Excellent. Yeah. This is like an aside. Okay, but look. So you're getting very excited? I'm getting very excited. It's so lovely how these things work out. So we get from here, through the aside, di-f di-t is b times di-f di-x. And I've just got a couple extra terms here, 2 extra x's here and an extra x here. X squared minus x. So we don't have the probability generating function, but we have a partial differential equation that describes the probability generating function. And if we could solve it, we'd have it, et cetera. So we can do all kinds of neat things here. So this is PDE, describing the time evolution of the Pgf Yeah, and then we do all sorts of things because then we can evolve it out in time to a certain time that we care about, to a time when the population bottleneck occurs, whatever. Right? And if this is what we get from a pure birth process, but you can imagine all the different processes that you could put in and how they change in time, and then you can derive these equations and go from there. If you would like a challenge, this is your brain, this is the universal symbol for like challenging problem. Go and redo all that for a birth-death process. So how would it look? A birth-death process. So obviously, you introduce deaths at constant rate d, and then do all those steps and see where you get. Okay. More questions? Yeah. So you mean you're imagining a branching process embedded in a big population, like a big population of wild type, and we have, you can do that. So there's no way to include the wild type population in a branching process formulation, but the rates could change. So if you knew some deterministic thing about the wild type population, so competition is getting fiercer and fiercer as time goes on, you could have these rates, like the birth rate could change in time. So you could have, instead of B as the rate, or B could be a function of N, where N is some deterministic function of T. So there are ways to fold it in for sure, but typically you might go to a diffusion approximation once you start to care about if the wild type are interacting with the mutant, which I will talk about soon. More? Okay, I think everyone needs to stand up and stretch, literally. We have half an hour left to go. Stand up and stretch, breathe, tell a joke to your neighbor. Leave if you're really, really offended and bored by this whole thing. Okay, fate of rare mutations. Here we go. Last little bit. So because we all know where we're going and you've all had some PopGen before, you started to ask questions already about these extinction probabilities, and I framed all my examples about the fate of rare mutations, but we haven't really talked more generally. So the kind of canonical plan was that I teach you the math, and now we're going to do the application, but it's been folded in all along, of course. So fate of rare mutations, you probably have this basic idea already. There's some, say, de novo mutation, or at least rare mutation of some particular type. It could be an indel. I'm not assuming it's a SNP. Something new has happened in the genome, and it's rare, and let's say, for example, a single copy. And then you've seen these kind of pictures, right? So here's time, and here's the frequency of the rare allele that we care about. It starts, it could be 1 on 2n. I like to present math at the beginning for the haploid world because it's just one intellectual step easier. So we're going to start at 1 on n, and because of the vagaries of the offspring distribution, sometimes it just goes extinct right away. Sometimes it might take a while to go extinct. So the frequency changes over time, and sometimes it might go to fixation, right? That's the question we care about. So these guys are all extinctions. And this is fixation, where that's obviously frequency 1. What do I want to tell you? You know, because you know Haldane's result 2s, that for a generic beneficial mutation that we might see in the wild, usually we'd expect it goes extinct, right? Even if it's good. Not as true in lab populations, where we see huge benefit mutations, right? S equals 10, but the generic thinking is that a lot of beneficial mutations go extinct, and this is rare. I've already introduced the notation. X is the extinction probability. I'm going to use pi to be 1 minus x. And there's a little subtlety here. Pi, we usually call it the fixation probability, but I'm going to put that in quotes. Because these situations can happen where the mutation doesn't go extinct, but once it gets to a high density in the population, maybe there's some stable polymorphism for some reason. So it hovers around 0.4 and stays there for the rest of the time, right? Or maybe, who knows, other things happen, other mutations come in a clonal interference situation. So it may not reach fixation, even though it doesn't go extinct. So really, we want to use this to avoid the question of what happened once it got big. So just because it wasn't eliminated by drift when rare, doesn't mean that it always fixes in real life. Yeah. That's the next. Yeah, that's the next thing on my notes. Yes, excellent. And so, because of this problem, you may have read of an establishment probability, and this is a way, just a new word that's a way around this issue. Maybe I'll fit it here. If it gets big enough that we can sort of say with some certainty it's not going to go extinct anymore, we say it's established. So there's some threshold, it will no longer go extinct by drift. And once it exceeds that threshold, we call it established. Right, so the question is, do we know that once it crosses that threshold, it will never go extinct? No, so you have to pick some kind of confidence interval, like you'll say, I'm happy with 99%, and I will call it established if there's a 99% probability that it won't go extinct anymore. But there's always a tiny probability that even if it got to 90, it would still go extinct, right? Yeah, so you pick some arbitrary threshold. So it's, yeah, it's not as clear a definition as these others. But this is a pretty clear definition. Yeah.
An establishment scenario would be different for different values of S, right?
Yes.
A beneficial mutation.
And N.
And N, yeah. You're reasonably unlikely not to be lost
Yeah.
versus neutral.
Yeah, exactly. Yeah.
So provided that there is only drift action, the expectation is that the allele will always lead to it. Some alleles will always lead to it.
The question is, will some alleles always go to extinction and some always go to fixation? Yeah, that's not quite. Actually, maybe the next little thing that I talk about might clarify this.
Yeah.
Yeah, we'll see. If not, you can ask again for sure. Yeah.
So when you're talking about established, it's like giving a threshold that it overcomes drift. So with your population size, you already know whether it's drift or it's like I don't get that part. How threshold is because it's frequency of alleles in your population. The population size is large.
So that it would be a whole lecture, so I'm not going to give it, but this threshold that you pick will depend on your own confidence. 99% I'm happy, 90% I'm happy. It will depend on the population size, and it will depend on the selective coefficient of your allele. And we could do the math to figure out how to write that formula. Yeah, but your intuition is exactly right. It will change. It depends on all these things.
But I guess the important thing that you're saying, though, is that even in a big population where selection dominates, like your point, is running away from the number 0 is still a drift problem. Right? In a billion individuals where selection can happen, the effect is big. It doesn't matter if you're one copy, but you still have to run away from the number 0 as much as you would until you get to really small populations. Is that fair?
Yes, in fact, somewhere here is a note to say, so yeah, this idea, because maybe what I started to hear and what you're talking about is that in big populations, drift isn't important, selection is important, and in small populations, selection isn't important and drift isn't important. But it's a little bit more subtle than that, right? Because, well, just what you said, Chris, really, that we can still have extinctions. So with the branching process, we assume the population is huge, infinite, in fact, and we still have big extinction probabilities, right? And that's drift. So what I wanted to say was that there's this confusion in the way the words are used, and just for the students, drift, we typically think of drift, and when you first get introduced to drift, we have a certain frequency of the allele, like 0.8, and stochastic sampling from generation to generation will change that 0.8, and we call that drift. But also, when you have this frequency of the allele that's 1 on n to start, and it changes here stochastically, we call that drift. But this is not because of the sampling from one generation to the next. This is from the offspring distribution, right? Whether this guy had 0, 1, or 2, according to our f of x, and whether their offspring had 0, 1, or 2. You could say that the offspring distribution is from the sampling, but that's a little bit roundabout, right? So there's kind of 2 different ways to think about drift. They're both called drift. So the kind of drift that this fluctuating around 80% drift, that's gone in the infinite population, but this drift is still there. Okay. So back to who fixes and who doesn't fix. I wanted to draw the DFE. DFE. So the distribution of fitness effects of mutations. I assume you guys have seen some of sketches of these, at least in your intro pop gen. So here is S, this is 0, this is -1, which is special because if S is -1, these guys are lethal. So there's some fraction of mutations, which are of course understudied for obvious reasons, that are lethal. And then we expect there's some kind of tail of deleterious mutations. Maybe there's some hump of relatively neutral ones, and then some different tail of beneficial. What did I want to say? And what we consider neutral, right? If n is very large, selection is strong. And here, I should have used a different color, pink. Those guys are sort of effectively neutral. But if n were smaller, selection wouldn't work as well. And we'd have a bigger range of what we would consider neutral. And we will get to how we define those ranges a little bit. And then who can fix which of these mutations along here have a chance of reaching fixation? The ones that are at the tails. Oh, that's so either deleterious or beneficial, but not neutral. To reach fixation. Fixation or loss. Yeah. Okay. Yeah. So for fixation, everybody has a chance, even the deleterious ones, even the neutral ones, right? These beneficial ones obviously would have a higher chance of fixation, except the lethals. Obviously the lethals. So everybody except the lethals has a chance to fix. Now, as the population gets bigger and bigger, the chance that the deleterious mutations fix gets smaller and smaller, right? And in the limit of infinity, which is what we do with this branching process, anything deleterious, their fixation probability goes right down to 0. So maybe having this picture in your head will help. Yeah? Okay. And then I'm going to sketch what I was just talking about a little bit, the fixation probability, even though we haven't done all the math yet. I think getting the picture in your head is really nice. So maybe for your notes though, all but lethal can fix. But if n is large, pi for the deleterious ones goes down or goes to 0 in the limit. Okay, what's pi for the neutral mutations? So neutral mutation, we start with a single copy in a population, haploid asexual population of size n. What's its fixation probability? Neutral mutation. So S is 0, 1 over n. 1 over n. Probably got that as if you did the beginning. Yeah, so this is 1 over n. The neutral mutation's 1 over n. Right? Because everybody, it's just a random walk. If you start at that frequency, yeah. Okay. So here's one of my last questions for you. Now, first, let's write up here again. Pi for beneficial mutations. 2s, excellent. Okay. So then here's the question for you. It's a challenge question, but you can do it. You should do it right now. So I have a population of size 100. I have one copy of a new mutation. And it's beneficial. Its S value is 0.001. What's its fixation probability? 2 times S is another guess. So we're getting 2 times S would be 0.002. 0.012. Yeah, you see why it's tricky? Yeah, so let me draw a sketch for you that I think will give you the right intuitions about this. So if I had an infinitely tall blackboard, it would go right under. This sketch belongs right under that sketch over there. So let's do S, 0. Okay, 2S. Line 2S is here. And the y-axis is pi. Thank you. 1 is here. Should make use of all my colors. So when S is very large, obviously we're very close to 1, asymptotically. When S is small, somewhere in here, we go along the line 2S. When S is 0, we need to be at 1 on n. Let's say it's there. But notice that 1 on n is much bigger than 2S, right? It's because this mutation is in that neutral zone. So the curve is going to go something like this, right? So 2S is a good approximation for some range of S's. This is why it's confusing. I mean, it confused me when I first learned this. I remember being confused about exactly this point. So this is your S small region, but it doesn't go all the way to 0, because pretty soon you get to the point where 1 on n is bigger than 2S, which is the example that I gave you here. And so, I mean, physically what's happening, this mutation, drift alone, is a much bigger effect than the selective advantage. And so I think your approximation is probably quite close. I mean, there's some little addition to 1 over n, something. Yeah, there's some small addition to 1 on n because it has some small selective advantage. So it's, we're somewhere in this range. So it's, we don't know exactly, but it's not 2S. It's going to be something like 1 on n plus some epsilon. So the neutral zone, this also helps us see where is the neutral zone going to be. So I was saying we consider what's considered neutral. What makes sense from here? Where would you start considering S neutral? When you start getting close to 1 on n, right? Or cross 1 on n. Yeah. So when we effectively neutral, when 2S is getting close to 1 on n, which gives us this, which you've seen in earlier talks today and yesterday, I think. This is a really common threshold for neutrality. And I often find there's all these little rules of thumb about n and s and all these various expressions that you need to remember. But this one, if you just can remember this picture, you can always rederive that in your head instantly, right?
Essentially.
Yeah, I guess the predictions are the same from both models.
Right.
Yeah. I guess you could say the forces are equal, yeah.
I mean, there's not a hard line.
No.
You'd rather be a mutation with an S of 0.005 than 0 or minus 0.005. Like those would have different.
Yes.
They're close to neutral, but one is a little bit better than neutral, one is certainly a little bit worse.
Yeah. But I think that's good. That's a neat way to think about it, actually. Okay, I have apparently 2 minutes, so I think I'm good for this section. Let me just double check that I didn't have other notes that, I really need to tell you. Yeah, I think I'm good. More questions? Okay, so next time I'm here, we will learn diffusion approximations. And we will also, here's some other homework. Next time I'm here, we will talk about when we will use a branching process, what are the advantages and the disadvantages of a branching process. So you can think about that too. Okay, thank you. See you at dinner.